Students, I hope you had a good weekend. I'm making this other video here for you on chapter 6, and we left off talking about trying to figure out something about the depositional environment where sedimentary rocks form by looking at fossils, and for detrital sedimentary rocks, size, sorting, and shape. But we didn't talk about sedimentary structures yet. If you get a chance, read through your book about sedimentary structures. Here's a list of the different ones I'm going to cover. We've got beds. We know sedimentary rocks are deposited in beds, such as beds of sandstone, beds of limestone, and the boundary between different beds, we call them bedding planes. Bedding planes are indicative of a change in depositional environment. For example, if you have a shale bed that was formed in a lake and it's overlain by a limestone which is formed in the shallow ocean, what that tells you is at that particular location there used to be a lake, and then sea level rose and limestone was deposited on top of that old lake due to what we call a transgression, a global rise in sea level due to global warming. But we haven't talked about graded bedding, cross bedding, ripple marks, and mud cracks, and biogenic sedimentary structures, which are interesting clues. I mean, if you find these sedimentary structures inside of sedimentary rocks, they're a dead giveaway as to where that sedimentary rock formed. Let's take a look at some of these. The first one we're going to talk about is graded bedding. Graded bedding. Now, what is graded bedding? Well, in order to understand what graded bedding is, we have to look at the coastline. Some parts of the country we call it the shoreline. It means the same thing. Over here to the right you would have land, and then you have the continental shelf, and the continental shelf is the shallowest part of the ocean. Then we have a steep drop-off, a steep slope, a steep drop-off called the continental slope. And then as you go further offshore, you reach something called the continental rise. What's the continental rise? Well, the continental rise is this little bump of sediment on the base of the continental slope. Once you get beyond the continental rise, you're in the deep ocean. So, bottom line is, let's take a look here and do some Oceanography 101. Here's your typical coastline. Here's the land, and there's the continental shelf, the shallowest part of the ocean. Then you have the continental slope, and then this bump here at the base of the continental slope is called the continental rise. Once you go seaward of the continental rise, you're in the deep ocean, and that's called the abyssal plain. The abyssal plain can run for thousands of miles, and it's really flat. There's almost no topography. It's like Kansas, as flat as far as the eye can see. Oh, and also I'd like you to meet my dog. Here's my dog. Isn't she beautiful? Okay, but now you have to go, Jolie, because I'm doing this. And so there are these deep canyons that cut through the continental shelf and the slope, deeper than the Grand Canyon in many cases. Some of them are 3 to 5 times deeper than the Grand Canyon. And these are called submarine canyons. And I guess the first thing you should think about if you are of a scientific frame of mind is, why do we have these deep canyons? Where do they come from? Well, These submarine canyons come from sediment on the continental shelf. If you think about it, where does the sediment on the continental shelf come from? It comes from rivers. Rivers flow to the ocean, carry their sediment load, and deposit it onto the beaches. Then waves, currents, and tides redistribute that sediment. But sometimes the sediment starts to accumulate right here at the edge of the continental slope, and it'll slide down in these currents called turbidity currents. I'll spell that for you here. Let me show you what a turbidity current is. Turbidity current. So sometimes the sediment will just slide down at hundreds of miles per hour going down the continental slope. And when that occurs, the sediment is like a knife carving through hot butter, or soft butter would be better, and it just carves out these canyons. So these turbidity currents carve out these canyons. And the sediment ends up being deposited onto the continental rise in graded bedding. Let me show you what that means. So here's the sediment from a turbidity current sliding down the continental slope, and the sediments are deposited on the continental rise, and they form this structure called graded bedding. So within a single sedimentary bed, you will see a precipitous, a sharp increase in grain size as you go from top to bottom, or better yet, we can say, since we're working in historical geology, from bottom to top, the grain size finds, so that you'll find coarse pebbles on the bottom of a graded bed. You might find sand on top of that, and even smaller than sand is silt, and then the mud will be on top of that. So within a single bed, you see a decrease in grain size, and this is called graded bedding. Graded bedding. That's our first sedimentary structure. Let's take a look and see what graded bedding looks like. Okay, this picture here shows you two graded beds. You can see within this bed, you get finer and finer particles, finer and finer sediment, until you hit the next graded bed. So a turbidity current may have deposited this graded bed, and maybe 5,000, 10,000 years later, there was another turbidity current that deposited the next graded bed. Bottom line is, if you find graded bedding in sedimentary rocks, ladies and gentlemen, what it means is you're dealing with a continental rise depositional environment. That's a dead giveaway that those rocks were formed on the continental rise. Okay, so I'm not going to keep belaboring the same point, but don't forget, graded bedding means you're on the continental rise. Now let's take a look at the next sedimentary structure, which is high angle cross bedding. Okay, what is high angle cross bedding? Well, if you've ever paid attention to rocks, driving by the road, you might have seen something like this. Notice how these, here's a bed, and the layers within each bed are steeply dipping. They're steeply tilting. Here you can see it up close. See how here's a bed, and then within the bed, the tiny laminations, the thin layers within the bed, are tilted at a steep angle. Here's some more cross bedding. This is one bed. This is not a whole bunch of beds tilted. This is one bed. Within this one bed, you've got these tilted laminations. Laminations are very thin, anywhere from a 1/16 of an inch to an inch in thickness. So within a single bed, you have these laminations that are at an angle. This is called cross bedding. And cross bedding forms from sand dunes in the sand dunes. So let's take a look at sand dunes. If you've ever, think about it. Put your thinking caps on. Think about, where do sand dunes form? Well, sure, you're right. They form in the desert, but that's not the only place they form. Where else do they form? On beaches. So if you got why do they form? Because sand dunes are formed by the wind, and when the wind blows, here's a sand dune, for example. When the wind blows, the sand will move up one side of the dune and then move down, making these laminations that are at a steep angle from the overall sand bed that will be formed. So yes, cross bedding can form like this. Here you can see the sand grains moving up and moving down, forming these thin laminations, and this will become a single quartz sandstone sand bed with these thin laminations called cross beds. So when you have high angle cross beds, you're dealing with either a beach or a desert as a depositional environment. How would you figure out whether or not it was a beach or a desert that formed those sand dunes, that formed those cross beds? Well, I'll give you an example. When I was working on my postdoc, after you get a PhD, you get a postdoc, and I got a 1-year project to work on. I was working north of Norfolk, Virginia, up in Cape Charles, and I worked for the Department of Energy, and they had these cross beds that were 400,000 years old, and they wanted to know, did those cross beds form in the desert or on a beach? Well, what would you do if someone was paying you to figure that out? Well, my idea was this. I carefully looked at the cross beds, and I took out a hammer and a chisel, and I knocked out chunks of that rock. Then I went back to the laboratory and cut thin slices out of that rock using a diamond-edged blade. Then I rubbed those thin pieces of sand until they were thin enough so light could pass through them. Then I put them under a microscope. And my idea was, if I found little seashells, for example, in between the sand grains, it probably formed on the beach. If I found desert tortoise fragments, bone fragments, or scorpion spines, or other creatures that lived in the desert there should be remnants of them between the sand grains. And I, in fact, did find ancient oyster shells there, fossils, in between the sand grains, and I was able to determine that the correct depositional environment for those cross beds was a beach. But the fact that there was steep cross bedding, told me that I was dealing with either a beach or the desert, so that helped a lot. The next thing we want to look at as far as sedimentary structures go are ripple marks. Let's take a look at ripple marks. Okay, I'm sure you've seen these things before. Think back to when you were a little boy or a little girl, and your parents took you out to the river. I'm sure you've been to the river and you've seen these before. So we know that these ripple marks can form in the river, along a river. But have you ever been to the beach? You also see ripple marks on the beach. So ripple marks, like the ones you see here, are either formed in a river or on the beach. And I want to show you how to tell the difference between ripple marks that form on a river versus those that form on a beach. Okay, and the way you can tell is when you look at the ripple marks that form in a river, they look like this. They have a gentle side and then a steep side, a gentle sloping side and a steep side. And the steep side points to the direction that is downstream for the creek or stream you're looking at. But if you look at the ripple marks that form on a beach, they look like this. Both sides are the same. We call these symmetrical ripples. Symmetrical because they're the same shape on both sides. River ripples, in contrast, are asymmetrical. And I'll spell those two words for you. Symmetrical ripples. Symmetrical ripples form where? On the beach. Asymmetrical ripples form where? For rivers. And when I say rivers, I mean creeks and streams too. So why do we form symmetrical ripples on the beach and asymmetrical ripples in rivers? Well, the reason why is because if you think about it, rivers are formed by unidirectional currents. Uni means one direction. Rivers only flow downstream. They flow in one direction. And that's why we form these asymmetrical ripples. But when you're on the coastline, then you're dealing with bidirectional currents or two-directional currents. The high tide comes in, the low tide goes out. The high tide comes in, the low tide goes out, forming symmetrical ripples. So please don't forget, ripple marks mean they're formed by rivers or along a coastline. Asymmetrical ripples form from rivers. Symmetrical ripples form from what? That's right, the coastline. Now, next thing I want to show you is mud cracks. I'm sure you've seen mud cracks before. This is what they look like. You've definitely seen mud cracks before. And I know I can't see your face because I'm doing this online, but I saw you yawning, and mud cracks, they are not boring. They're exciting. I remember as a young boy, I would have mud cracks right next to my poster of Farrah Fawcett on my ceiling. No, that's how, when I saw mud cracks for the first time, I could not sleep at night. All right, actually, mud cracks are not that exciting, but where do you find mud cracks? At lakes that have dried up, right? So when you're dealing with mud cracks, these get preserved in the rock record. Let's take a look at mud cracks. And see, you can see these actually get preserved in rocks. And what does that tell us? It tells us that conditions became dry. Crossbedding formed by the wind. We talked about that. We talked about ripple marks. This shows you symmetrical ripples formed in the shallow ocean. And here's your mud cracks. Next thing we're going to talk about is bioturbation. And I found a lot of these, and so is my. Recently went out with my friend Wesley Hayes, and he found a lot of these. And these are little tunnels that are burrows that organisms dug underneath the sea floor, or sometimes under a lake floor. And you could tell by the shape of these burrows and how big they are, who made them. So that's actually a fossil if you think about it. It's not a body fossil, it's a trace fossil. And we can find these when you go fossil hunting in Tennessee, because Tennessee has been covered by the ocean 3 times. And you can see the burrows that were built by these ancient organisms. And sometimes if you're lucky and you pay close attention, you can find the body of the animal that made these tunnels inside of the tunnel. Okay, I think that's enough. Please watch all these videos twice. Take good notes. We're going to have a test coming up on, let's see, the next test is going to be on March the 1st at 7 p.m. So have a wonderful week.